All right, guys. Next topic, 2.14. Logarithmic function, context, and data modeling. So there's two parts to this. One we will be doing without a calculator, and the other part you will need the calculator. So if you have it handy, you should have it in front of you when we get to that portion. All right, so this is a graph for the average salary for a church pastor across the U.S. And it shows that it increases as the size of the church increases. So as the number of people increases, so does the pastor's salary. The graph above shows the average pastor salary for various church sizes. So we can clearly see that a pattern, in the data. But the models that we've used previously are not appropriate, right? And if you remember the models that we've done so far, we've done linear. Obviously, this is not linear. We've done quadratic, cubic models, right? Quartic. I'm not going to put them all, but basically all the types of polynomials. We've done exponential. I think we've done rational. All right, and none of these work for this model. It doesn't look like a line, it doesn't look like a quadratic, cubic, and so on. Now the graph above displays a large rate of change initially. So at first it grows very rapidly, but then as the church size increases, we see that the rate of change gradually starts to decrease. That means the slope from here to here becomes smaller, right? So the slope here is much, much higher than at the end. So you notice that the data above appears to be what we are dealing with right now, which is logarithmic. So just as we've seen with other types of functions, linear, quadratic, and exponential, many real-world scenarios follow logarithmic patterns. Outside of salary data, in the graph above, logarithmic patterns are found in the way we measure earthquakes, sounds, acidity, okay, if you remember in chemistry, pH, and many other contexts, and sound when it comes to decibels. And then earthquakes with the Richter scale. All right, so we'll be doing examples with these. As a result, we have a need to create logarithmic models for these types of data. Now, logarithmic function models without a calculator, we have to, we're given a set of data. If the input values, right, the x values, change proportionally. So if x is proportional, okay, which means changes with multiplication or division, or multiplication of a fraction, over equal length output values. So the output values, y, the y values are equal length. Remember, this is the inverse of exponentials. Then a logarithmic model is appropriate. So a logarithmic function model has the form of y equals a plus b ln of x, or y equals a plus b log of x, base 10, where a and b are constants. And of course, we have to remember that b cannot equal 0. If b equals 0, 0 times log x is just 0, so it's not a log function. So let's put this into an example. So here's our selected values of a logarithmic function L, and they're given right here. So they're telling you that this is logarithmic. You don't have to figure it out, because you can't really figure out a logarithmic function with just two sets of data points, all right? But they're telling us that this is a log function or a type of log function. Now, specifically, they're telling us that this is actually a log base E function, which is ln. And it has this form. L of x equals a plus b ln of x. So we're going to use the given data to write two equations that can be used to find the values for the constants a and b in the expression. So this is the same stuff that we've done before, right? I'm going to use one set of data points, so L of 2. So I'm going to use the 2, 3. And I'm going to plug it in. Right? Because the 2 goes in for x. And the L of 2 is basically the y value, which is 3. So 3 equals a plus b ln of 2. So that's going to be one function that will help us figure out a or b. And then the other one is the L of 5 is equal to a plus b ln of 5. And the L of 5 is the y value of L of 5, which is 7. So 7 equals a plus b ln of 5. So these are the two equations that we're going to be using to find a and b. So now to actually solve and find a and b. All right, so this is a little bit different because normally when we do this, one of the variables disappears, right? And we are able to just solve for the other variable. But in this case, ln of 2 is not 0, so the b does not disappear, and neither is ln of 5. ln of 5 is not 0. So we need to use a different method. And the method we're going to use is from Algebra 1. We have these two equations. We have this guy and this guy. So we know that these two equations should give us the same a and the same b. So basically what we can do is we can set up these two equations as a system because they do work together, right? So 7 equals a plus b ln of 5. So these are the two that I'm going to be using. And once we set this up, I'm going to choose to subtract one of them. So I'm going to subtract the top from the bottom. And what that will do is it's going to eliminate the a, right? So I'm going to use elimination and subtract them. And that way I can eliminate the a. So 3 minus 7 is going to give us -4. A minus a is gone. That's the idea of elimination. And then you're left with b ln of 2 minus b ln of 5. So b ln of 2 minus b ln of 5. Can't really combine these yet. All right. Now we're going to take this part of the equation and we're going to do the next step. We want to solve for b, right? So because there's a b in both of these terms, I'm going to factor out the b. So I got ln of 2 minus ln of 5 equals -4. Okay. Next up, I'm going to use what I know about my log rules. And since these both are ln, I can use division and set this up as ln of 2 over 5. Now remember, ln of 2 over 5 is a number. It is a numerical value, just not one that can easily be found. So now when we solve for b, the last step is going to be to divide by this number, ln of 2/5. Divide by ln of 2/5. So that's gone. And so now we have b is equivalent to -4 over ln of 2/5. And if it was a problem without a calculator, you would leave it just like that. All right, but with a calculator, once we solve this -4 divided by ln of 2/5, we got -4 divided by ln of 2 divided by 5. And our answer is 4.36542. So 4.365. So 4.365. So B is equal to 4.365. And then now that I have B, I can easily solve for A, right? I can pick either one of these equations. So to solve for A, let's pick the first equation. So we got 3 equals A plus 4.365 times ln of 2. 3 minus all of this, 4.365 ln of 2 is equal to A. When you do this in the calculator, you end up with -0.0258 is equal to A. So these are our two answers. All right, moving on. Next up, you're going to need your calculator out. Now, unfortunately, I don't have a TI Inspire on this computer to show you, so you're going to follow along with my words. So here is a table for the church size and the average salary of that original graph, okay? From the beginning of notes, related church size and the average salaries. We're going to use the regression capabilities in our graphing calculator to find a logarithmic function, okay, model for the data above in this form. S of P equals A plus B ln of P, where P represents the church size and S is the average pastor salary. So if you remember, what do you need to do in the calculator is you're going to need to go to a new document. And then in new document, you have to go to add lists and spreadsheets. And then once you're in there, you're going to plug in your data. So under A, I'm going to go up to A, and I'm going to call that my church size. So I'm going to actually just call it S. And where B is, that's going to be my, sorry, not S. So under A, that's going to be my input values, which is going to be the P, right, representing the X. So I'm going to call it P. You can call it whatever you want. And then for B, that's going to be the S, which is the salary. I'm going to input my data all the way down. So 75, 120, 250, 300, 450, 650, 900, 1500, 2500, and 5000. I'm going to do the same thing for the output values, which is 42, 58, 70, 79, 88, 95, 110, 125, 138, and 175. Make sure you didn't miss any values, all right, because that's going to be very important. Now, after we input the data, you're gonna go back to control doc, and then you're gonna go to data and statistics. So you're gonna press control doc, and then from there you're gonna go to data and statistics now, so that you actually have points on your screen. You're gonna click to add the variable for the x-axis, and that's gonna be my p values. And you're gonna click to add the variable for the y-axis, which is gonna be the s data points. And then once you graph it, you end up with the same graph that we had right here, okay? So add the variables to x and y. And now when you have that, you can go back to menu. You can press menu, go to analyze the data, which is number 4. And you're gonna go to regression, which is 6, regression. And of course, this is a logarithmic regression, so we're gonna show logarithm. Which is number 9. And as soon as you do that, you end up with your log function. And the log function that I got is y equals negative 91.542 plus 29.088.9088 ln of x. And your y, if you remember, is your s of p, and your x needs to be labeled as p so that we follow what they told us to do. Now that we have our function, we're going to use the model that we found in part A. And what is the predicted annual salary? So what is S of P when P is equal to 500 people? So basically you're solving for S of 500 from your using your function. All right. Now, I know that there is a way for you to just use the calculator and basically select a point, I think. Maybe one of you guys can figure that out. Maybe if we plot a value, 500. So when you do that, you kind of get the point, but not really. All right, so until we figure that out, we're basically gonna plug in our point into our formula that we just got. And once you do that, you should end up with 94.3295. And what is the unit for the salary? It's right here in thousands of dollars. So it's 94.325 thousands of dollars. All right, example 3. The most common and preferred method to measure sound intensity levels is in decibels. The sound intensity level B in decibels of a sound having intensity of I, where I is in watts per meter squared, is modeled by the function B of I equals A plus B log base 10 of I. All right, so the input value is going to be your watts per meter squared, and your output value is known as your decibels. And A and B, of course, are going to be your constants. The sounds of noisy traffic has an intensity of 1 times 10 to the negative 5th watts per meter squared. So this right here, this number that they just gave us, is our intensity. And it corresponds to 70 decibels. So this is our B of I when I is 1 times 10 to the negative 5th. A loud concert has an intensity of 1. So this is our second point for I, and 120 decibels. So use the given data to write 2 equations that can be used to find the values for constants A and B. So the 2 points that we have, basically, we got our B of I, right? So the 2, we got B of 1 times 10 to the negative 5th is equal to A plus B log of 1 times 10 to the negative 5th. And we know that this is equivalent to 70 decibels. And then the other information that we have goes with B of intensity 1 is equal to A plus B log of 1. And of course, B of 1, they are telling us, is 120. So these are the 2 equations that we're going to use to find the values of A and B. Okay? Now, this one's slightly different than the one before. And the reason is because we actually have a log of 1 in this problem right here. And we know that log of 1 is equal to 0. So from this problem, we know that 120 is equal to A plus B times 0. So what happens to B in this problem? B times 0 is 0. So 120 is equal to A. So finding the values of A and B, I just found the value of A. So A is 120. And once I find A, which is 120, I can use that in the second equation. to find b. So 70 equals 120 plus b. Now remember, 1 times 10 to the negative fifth is basically the same thing as what? Let's see if the calculator gives it. All right, 0.000001, right? Or we can write it as 1 over 100,000. All right, and now we're just going to solve this like we would any other log. We're going to subtract 120. So 70 minus 120 is negative 50 equals b log of 1 over, or 1 times 10 to the negative fifth, since we may have a calculator with this. All right. We got to isolate the b, right? So we're going to divide both sides by log of 1, or 0.1 times 10 to the negative fifth. Could have done this a lot easier, and I'll show you how in just a second. But negative 50 divided by log of base 10, 1 times 10 to the negative fifth, gives us an answer of 10. So if I divide both sides by log of 1 times 10 to the negative fifth, divide by log of 1 times 10 to the negative fifth, b is equal to 10. All right, and the reason that is because, remember, this is a base log of 10. So 10 to the what gives us 1 times 10 to the negative fifth. It's just negative 5. All right, so without a calculator, I could have really written that second part as 70 equals 120 plus b. Instead of log base 10, 1 times 10 to the negative fifth, I could have just said times negative 5, because that's what that equals. All right, so fun fact, you guys can read that on your own. And then the last part is about the human eardrum. It can burst when sounds reach an intensity level of 1 times 10 to the fourth watts per meter squared. According to the model found above, what is the predicted number of decibels required to burst a human eardrum? So the model that we found above follows the equation. B of I is equal to A, which is 120, plus B, which is 10. And it was log base 10 of I. So this is the function that we solved for. And now we have an input value for I. So B of 1 times 10 to the fourth is equal to 120 plus 10 log of 1 times 10 to the 4. So what does this equal? Well, remember I just told you, how do we solve this guy? Little side work here. We got log base 10 of 1 times 10 to the 4 equals what? So 10 to the what equals 1 times 10 to the 4. 1 times 10 to the 4 is just going to be 10 to the 4. So 10 to the what equals 10 to the 4? That's 4. So what does this equal right here? 4. So 120 plus 40 equals 160, and then the unit for the B is decibels. So what is the predicted number of decibels required to burst a human eardrum? If you have this kind of intensity, 160 decibels. All right, that is it. And we'll do the practice sheet in class.